So we're going to talk about this Dirichlet series, the sum n from 1 to infinity of the sum of divisors function, sigma sub w and chi, will be a Dirichlet series in S. So recall that the sum of divisors function, sigma sub w and chi, is defined to be the sum over the positive integer divisors of n, and the terms are going to be chi d to the w. So to evaluate this Dirichlet series, there are a couple ways to do it, but we're going to do it by writing it as an Euler product. So this is going to depend on this observation that sigma sub w and chi is multiplicative. So let's see that now. So sigma sub w, I'll say p to the r n times chi, where the GCD of p and n is equal to 1, so these two things are coprime. You can write this as, okay, so the sum of divisors, d divides p to the r n of whatever, and the sum over divisors, well, what are the divisors of this product? This is going to be a sum over d divides n, and I'm going to say this integer k going from 0 to r of some power of p. So it'll be chi of p to the k d times p to the k d to the w. So this sum is looping over all the divisors of n because we're assuming that they're coprime, and then you can see just multiplying out that this is exactly equal to the sum d divides n of chi d to the w times the sum k goes from 0 to r of chi p to the k p to the kw, and this is of course the sum over the divisors of p to the r, right? The divisors of p to the r are just the powers of p less than r, so this is sigma sub w n chi, and this is sigma sub w p to the r chi. So we see that this sum of divisors function is multiplicative, and what that means is that this Dirichlet series, sum n from 1 to infinity of sigma sub w n chi over n to the s, we can do the usual Euler product thing and say, well, for each prime, pick the power of p that you need to build n, and what you end up getting is the following. So here you're going to have this infinite sum over all the powers of p at each prime. Etc. Now, for each of these sum of divisors functions, we can write it just using its definition. We know what the divisors of some power of p are. This is going to be 1 plus, and then here we have 1 plus chi p times p to the w over p to the s, and then the second term here is going to be 1 plus chi p to the w plus chi p squared p to the 2w all over p to the 2s. The third term will be 1 plus chi p p to the w plus chi p squared p to the 2w plus chi p cubed p to the 3w all over p to the 3s plus dot dot dot. So here let's just clean these up and let's write them as infinite sums or finite sums in the case of these numerators. So this is a sum. So it's a product over p times the sum over the powers of p. So I'm going to say r goes from 0 to infinity, and then each term is 1 over p to the rs. That's the denominator. And then the numerator is going to be a sum. K goes from 0 to r of chi p to the k times p to the kw. And now these are geometric series, so it's going to be product of primes, sum r from 0 to infinity, 1 over p to the rs, and then evaluating this geometric series, just 1 minus chi p to the w to the r plus 1 over 1 minus chi p to the w. And now we have the sum over r to deal with. This denominator here doesn't depend on r, so let's bring it out. So it's product over primes, 1 over 1 minus chi p to the w, and then sum r goes from 0 to infinity, and here we have two geometric series. So the first one is just going to be p to the minus rs, and then the second one is going to be, so let's take this plus 1 and let's bring it out. So chi p to the w, and then what we're multiplying here is chi p times p to the r, and we have a w minus s coming from here. Sorry, this yeah, we have a w minus s, and this is all to the rth power. Okay. Now evaluating each of these geometric series separately. So let's recopy the stuff in front. Product over primes, 1 minus 1 over chi p to the w, and then the first Euler product, or the first geometric series, gives us this 1 minus p to the minus s, and then the second one we have a minus, and then a numerator of chi p to the w, and then the common ratio 1 minus chi p to the w minus s. Now if we multiply, if we take the difference of these two things, just cross multiplying, so we get the same thing in front, 1 minus chi p to the w, and then here we're going to have a 1 minus chi p to the w minus s, and then here we'll have a minus chi p to the w times 1 minus p to the minus s, and then the common denominator is just the product of these two things, 1 minus p to the minus s times 1 minus chi p to the w minus s. And here we notice that there's some cancellation. This term here is going to cancel this term here. So we have a product over primes, 1 over 1 minus chi p to the w, and then right? Both of this is a minus chi p to the w minus s, and this is a plus chi p to the w minus s. So these two terms go away, and we get a 1 minus chi p to the w over, and then our denominator 1 minus p to the minus s times 1 minus chi p to the w minus s. And hey, there's some cancellation here. So we get this product over primes of 1 over 1 minus p to the minus s times 1 over 1 minus chi p to the w minus s. And this we can just recognize as the Riemann zeta function times this Dirichlet L function, but at s minus w. So this is what we end up getting for our initial Dirichlet series, i.e. the sum n from 1 to infinity of sigma sub w and chi over n to the s, at least where everything converges absolutely using the series definition. This is equal to zeta of s times L of s minus w chi. So that's cool. That's a nice representation. There's a little bit of asymmetry going on here, and this shift by w might seem a bit strange. A way to explain that is with this functional equation. So sigma, I'm going to write 2w here, n chi over n to the w is equal to chi n times sigma minus 2w n chi bar over n to the minus w, at least when n and I'm going to write uppercase n. This is the modulus of chi. When these two numbers are coprime. So what that means is that this shift of w is kind of because we normalized wrong. One way you could write it instead is the sum n from 1 to infinity of sigma sub w n chi over n to the w over 2 times n to the 1 over n to the s. This is just shifting s by w over 2, and then using this formula we get zeta s plus w over 2 times L of s minus w over 2 chi. And this looks a little bit more symmetric, that's essentially because this is maybe the more reasonable way to normalize this sum of divisors function.